in this lesson, we're going to discuss how to find the net force on objects when there's forces acting in 2 dimensions. Most of the problems we've done so far, or you did in grade 11, the forces were all along sort of the same line, but in this case, they're going to be in more than one direction. So, for example, if we have this object, and we'll use this as the sort of the compass for all of these problems. We'll assume up is north, east is right. So if there's a force on this 250 kilogram object, one going up, one going down, one going left, one going right, what is the net force? You should be able to see what the net force is fairly quickly. You should see maybe that this 25 and this 25 are going to balance each other out. So the net force in that direction, in sort of the north-south direction, is going to be 0. And then we can see in the east-west direction, the force going to the east is 25 newtons more than the one to the west. So we can see that the net force is going to be 25 newtons to the east, and that's the answer. But if we want to be a little more formal about it, this is especially important when we get more complicated questions. Let's use some correct terminology. So the first thing we have to do is we actually have to define our positive axis. So usually when we work with math, we like to define an x and a y-axis. So what we're going to do in any question like this, we're going to define our positive x and our positive y-axis. And usually we're going to make x be positive to the right and y be positive going up. That just makes it easy. That's how we read coordinates in math usually, and that makes it easier for us. So what we're basically looking for in any of these questions is we're looking for the sum of the forces in the x direction and the sum of the forces in the y direction. And the way we write that is like this, with this Greek letter sigma. It looks sort of like an E, but it's actually the Greek letter S, or sigma. It's a capital S. And that just stands for sigma, or sum. So that's the sum of the forces in the x direction. That's what that means. So the sum of the forces in the x direction is, well, remember we said that right is positive. So this force right here is going to be positive 100 newtons. And then this force right here, because it's going the opposite direction, is going to be negative 100 newtons. Or sorry, negative 75 newtons. So the sum of the forces in the x direction, remember that's what this means, the sum of the forces in the x direction is just going to be 25 newtons, right? And we know that the positive x direction is east, so we can actually just put here east to make it a little bit easier for us. And we're going to do the same thing for the sum of the forces in the y direction. Sum of the forces in the y direction. Well, that's just going to be, the upwards force here is going to be positive, right? Because we said y is positive going up. So it's going to be 25 newtons minus 25 newtons equals 0 newtons. And we don't need a direction when it's 0 newtons, right? So our final answer, the F net acting on that object, is just going to be 25 newtons to the east. And this is a vector, so we should put the vector arrow on top of it. Okay? So that's a pretty easy question. You could have done that question in grade 11, no problem. What happens if the questions get a little bit more complicated? By the way, if you did get a question like this and the answer was very obviously like 25 or something like that, you don't need to show all this work. I'm just showing you all this work because when the questions get more tricky, that's going to help us out. So we can do the same thing in this question. We want to find the sum of the forces in the x direction and the sum of the forces in the y direction. So why don't you try that yourself? You can pause the video here, try it yourself, and see what you end up with. So when you do this, this is what you should get to find the x and the y, the sum of the x and the y forces. In the x direction, the sum of the x forces is negative 55 newtons if you make right positive. What that means is that it's the negative direction. The negative direction we know is west. So the answer is 55 newtons west for the sum of the x forces, right? And the sum of the y forces is going to be 48 newtons north, right? Because it's positive and up is north. Okay, we can't have two things for the net force. We need one net force. So basically what this is telling us we have some net force in the north direction and some net force in the west direction. So what do we have to do to find a total net force? Well, you should realize this is the same thing as when we're finding displacement vectors, when we're adding displacement vectors, all right? And what we're going to do is we can see that if we go 55 newtons to the west and we go 48 newtons north, we're going to get a resultant vector between those two that looks something like that. So if we say this is 55 newtons and we say this is 48 newtons, we're going to have sort of a final triangle like that. And when we have to give the net force, we also want to give the direction. So I'm going to call the direction, the theta here, that angle in there. Okay? So when we do this, how do we do this, first of all? Well, we can find that the net force, the magnitude of the net force, F net without the little arrow on top, because this is just the net force, is going to be, well, we can do it using the Pythagorean theorem, right? 48 newtons squared plus 55 newtons squared. Take the square root of that, which is 48 squared plus 55 squared equals 73. Ooh, I happen to pick numbers that come out to an exact number. That's just a fluke. 73 newtons. Okay, so that's the magnitude of that. So that really right here is 73 newtons. And then we want to find the direction, right? To find the direction, to find theta, it's going to be tan inverse, or arctan, if you like calling it arctan, of opposite over adjacent, 48 over 55. And we make sure our calculator is in degree mode. We use arctan 48 over 55, and we get an angle rounded to the nearest degree. Two significant digits make sense for this question, of 41 degrees. So our final answer for this question is F net, with the arrow on top, it's a vector, is equal to 73 newtons. And then what direction is this? Well, it's west, 41 degrees north, right? West, 41 degrees north. There's our final answer. Okay? So hopefully you recognize this as the same process that we would do to find a displacement vector, right? And we're going to continue with questions that are a little bit more difficult now. So, how do we find the net force of acting on this 1,200 kilogram box, or whatever it is? We can do the same thing, right? We want to find the sum of the forces in the x direction, the sum of the forces in the y direction. And we always need to first show our convention. So this is going to be our positive x direction, this is going to be our positive y direction. We always need to show that, because you'll see there's going to be questions that we do later that we're actually going to choose a different convention. So in the question, this always needs to be there to show me what your positive x and positive y directions are. So in this question, we want to find the sum of the forces in the x direction, sum of the forces in the x direction, and we want to find the sum of the forces in the y direction, right? That's what we're looking for. So in the x direction, well, we have this force right here, right, which is negative 2.4 kilonewtons. Remember, it's negative because x is to the right, and this is our negative direction. Do we have any other forces in the x direction? Well, we have none directly in the x direction, but this force right here and this force right here are going to have components that are in the x direction, right? And that's what we have to be careful of. So essentially, we have to use the component method here to find out those components. So if we look, the component of this force right here in the x direction is going to be this part right here. And the y component is going to be this part right here, right? Just like for this vector here, the x component is going to go here, and the y component is going to go here. You might have drawn it the other way. You might have drawn the y component first and the x component second. I like to usually do the x component first, just because when we're doing math, we usually do x before y, and we just keep the process the same. If we do that, we should realize that this angle in here is going to be 50 degrees, right? Because it's a complementary angle to that 40 degrees. I find it easier just when the x component, when the angle is beside the x component, because then your x component is always the cosine of the angle, and the y component is always the sine of the angle. And it just makes the process the same each time, so you're less likely to make a mistake. So if you're comfortable with the component method, you should realize that this component here of this force, of the 1.7 kilonewtons, this length, this hypotenuse is 1.7 kilonewtons, but this x component here should just be that force, 1.7, and then it's going to be the cosine of 30 degrees of the angle, right? Because cosine is the one that's beside the angle, it's the adjacent side, right? And this one right here should be 1.7, the y component should be 1.7 sine of 30 degrees, right? If you're confused about that, I would go back and review the lessons on the component method, but you can also just draw a little triangle for yourself. If you draw a little triangle for yourself and do the trig, like sine is opposite over hypotenuse, cosine is adjacent over hypotenuse with your angle of 30 degrees in here, you should see why that this is 1.7 cos 30 and why this is 1.7 sine 30. So anyways, you try that yourself if you're not sure how to do it. This one right here, again, the cos is always the adjacent side, right? And the adjacent side here, if we use the angle of 50, is going to be 0.65 cos 50 degrees. And this side right here is going to be 0.65 sine 50 degrees, right? So there we go. We've broken down all of our vectors into x and y components, right? So now if we want to sum up the x components, we're going to sum up this one and this one and this one, right? Those are all our x components. I'd like to do them in red, the x components in red and the y components in blue. Just makes it easier to identify. So to do that, we need to also be careful of our signs, right? Because this one right here is going in the negative direction. We said that this is positive, so it's going in the negative direction. So we would do negative 2.4 kilonewtons. And then this one right here is also in the negative direction, right? Points to the left. So this is minus 0.65 cos of 50. And then this one right here, it's in the positive direction, right? Because it's going to the right. So plus 1.7 cos of 30. In the y direction, if we do them in the same order, I'm just going to include this one. Even though it doesn't have a y component, I'm going to put that down as 0, right? And then this one right here, vector 2, we can call this vector 2, force vector 2. It's going downwards, right, the y component. So it's going to be negative 0.65 sine of 50. And then this one right here, the y component is positive, it goes up. So plus 1.7 sine of 30, right? So the reason why I put the 0 here is because you see, this is vector 1, right? This vector right here. This is vector 2, or this one right here, and this is force vector 3, right? So you should see some similarities between the two. If you follow this process, you'll see that the x components are always the coses, and the y components are always the sines. That's if you make the x component or the angle beside the x component, right? So I just like lining them up like this. It makes it a little bit more neat. Also, instead of calculating these one at a time, right? Instead of calculating these values one at a time, we can actually throw this whole thing into our calculator and throw this whole thing into our calculator. The reason why that's good is because we don't have as much rounding error. The more you plug into your calculator and sort of round and then put that into your calculator, the more you do that, the more rounding error you're going to accumulate in the question. So it's better to do as much as you can in your calculator at one time, just to prevent that. Okay? So if you do these in your calculator, you should get, ta-da, there's the answers, 1.3456 newtons to the west for the x component and 0.35207 newtons north. Notice how I took a bunch of extra significant figures here. It's always a good idea until you get to the final answer to carry a few extra significant digits. So in this question, it makes sense to sort of, we're gonna finish up with 2 significant digits. So, you know, I just like to take sort of 4 or 5. 5 is a little bit of overkill. 4 would probably have been enough for this question. But anyways, so now with those 2 numbers, you should be able to find the final net force. So I want you to pause the video here, try to find that net force and the direction. unpause when you think you have an answer, and you can compare it to my answer. Okay? Pause it here. And there we go. There's my final answer. 1.4 kilonewtons west, 15 degrees north. Okay? So you should have got the same answer. Again, 2 significant digits is good for this question, and usually rounding degrees to the nearest degree is as accurate as we get. So I want you to try the last question yourself, this one right here, right? Something looks a little bit funny about it, right? There's a 160 Newton force going this way, and there's 2 80 Newton forces pulling this way, the same angle. Do you think those are going to cancel out? Is the net force going to be 0 here? I'm going to leave that up to you to try now. So pause the video, unpause the video when you want to see the final answer there, okay? So pause it here and give it a shot. So the final answer to this question is 9.6 newtons directly to the west. So hopefully you got that and you understand why it's not equal to 0. One last thing before we wrap up this video. I also wanted to mention that there are lots of different ways to organize your work for questions like this. One way I like to do it is with matrix form. And if you would like to do it that way, that's completely fine. Or if you have another way to organize the component method, that's fine. Just a quick refresher on what matrix form is. It would look like this. So I would draw it in a matrix where the top part is the sum of the forces in the x direction and the bottom part is the sum of the forces in the y direction. And I would just write each vector separately. So the first vector here, let's just do this one as an example, would be negative 2.4 and 0 would be the 2 components of it. And then you're adding to that the second vector, and the second vector has the 2 components right here, or right here and right here, right? So what that would look like would be negative, because it's in the negative direction, 0.65 cosine of 50 degrees, and the y component would be negative 0.65 sine of 50 degrees. And then we close that, and then sort of continuing on the white here, I would do the same thing for the last vector, whatever it is, 1.7 cos 30, blah, 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 blah. And then you just do the top all as one calculation and do the bottom as one calculation, and you get your final answer of what it would come out to be, whatever it is. What was it? 1.34, blah, 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 and 0.35, blah, blah, blah. So you get your final answer like that. If you want to organize your work in the matrix notation, that is completely fine as well. It's completely up to you as long as it's clear what you're doing. I do encourage you though to use the notation, the sum of f of x, the sigma f of x. That is notation that's sort of widely used, and you should be using that in this case.